Hey everyone, and welcome. Today we are tuning into a piece of tech that is, well, literally all around us. It's in our cars, it's used by emergency services, it's everywhere. We're going to break down exactly what frequency modulation is and how the whole thing works.
You've definitely thought about this, right? You're scanning through the radio dial and you see that little FM. It's one of those things we see and hear all the time, but have you ever stopped to wonder what's really happening behind the scenes to get that music to your speakers? Well, guess what? Today's the day we find out.
All right, so let's start at the very beginning. We're going to peel back the layers and get right to the core concept of what FMR's all about.
Okay, so there's your official textbook definition. Yeah, it sounds a little dense, I know, but the most important part, the real secret sauce, is right there. The frequency of a carrier wave is varied. So what does that actually mean? Let's use a simple analogy to make sense of it.
Okay, picture this, a perfectly calm, steady wave, just going along at a constant rhythm. This is our carrier wave. Think of it like a blank conveyor belt, just humming along, waiting for something to be put on it. It's got one specific unchanging frequency.
Now, let's think about the actual sound we want to send. The music, the voice from the DJ, whatever it is. This is our modulating signal. This is the information. So back to our conveyor belt, how do we get our message onto that moving belt?
And this is where the magic happens. Look at this. Instead of changing the height of the wave, its strength or amplitude, we change its speed. See how the height stays the same, but the peaks of the wave get squeezed closer together and then stretched further apart. That change in frequency, how often the wave goes up and down, that's the encoded sound. That variation is the message.
Okay, so we get it. We're messing with the frequency. But by how much? And how do we make sure those changes actually sound like the original song? Well, that's where a couple of key control knobs, if you will, come into the picture.
This first knob is called frequency deviation. And it's pretty simple, really. It's all about how far we let the frequency wander from its starting point. So if our carrier wave has a center frequency, the deviation is how far we push it up or down. A bigger deviation just means a wider swing.
Next up is the modulation index, and this is what ties it all together. See, it's not just about how far the frequency swings, but how that swing compares to the frequency of the sound we're trying to send. This ratio is super important because it basically defines the whole character of the final FM signal.
So, let's put that another way. The modulation index is basically a measure of how much information we're packing into the signal. A higher index means we're using a much bigger range of frequencies to describe the original sound. This gives you a more detailed, higher quality signal, but as you're about to see, there's always a catch.
Right. So all this frequency wiggling doesn't just happen for free. It takes up real estate on the radio spectrum. Every signal has a kind of footprint, and we call that its bandwidth. And this is really the key takeaway here. The more information you're trying to cram in, the higher that modulation index, the more space you're going to need on the airwaves. I love the suitcase analogy. A simple voice message is like packing a small carry-on. A complex, high-fidelity orchestra piece? Yeah, you're going to need a giant trunk for that.
And this isn't just guesswork. There's actually a famous rule of thumb for this called Carson's rule. It's a super handy formula that gives engineers a really good estimate of how much bandwidth they'll need for any given FM signal. It's like fundamental stuff in broadcast engineering.
So to sum this bit up, a higher modulation index creates what are called sidebands. You can think of these as little echo frequencies that pop up on either side of our main carrier. They all carry bits and pieces of the information, and the more sidebands you have, the wider your signal's footprint. And that leads us to two very different flavors of FM. Yeah, so depending on what you're trying to do, engineers have to pick between two main types of FM. And it all boils down to that classic trade-off. Do you want super high quality, or do you want to save on bandwidth?
And this chart just lays it out perfectly. Over on the left, you've got Narrowband FM, or NBFM. Check out how small everything is. The modulation index is tiny, the deviation is small, and so the bandwidth is narrow. This is exactly what you want for things like police radios or walkie-talkies. But then look at the right, wideband FM. The deviation is huge, the bandwidth is massive, and this is what gives you that rich, high-quality sound for music broadcasting.
So really, that's the bottom line. NBFM is all about efficiency. It's where when you need to cram a lot of different communications into a small slice of the airwaves, and just getting the message across clearly is the goal. WebFM, on the other hand, is all about that high-quality, immersive experience you get from your favorite radio station.
Okay, so we've established that FM,
especially wideband, can be a real bandwidth hog. So why is it still so incredibly popular? I mean, what's the big payoff that's kept it at the top of its game for all these years?
Well, the number one advantage, the absolute game changer, is how incredibly well it resists noise. Remember how we said the information is encoded in the frequency, not the height of the wave? That means things like static from a lightning storm or interference from other electronics. They just don't really mess with the signal. That immunity to noise is the secret to that crystal clear FM sound.
But, of course, nothing's perfect. There are some downsides. Like we've been saying, that beautiful sound comes at a cost. It eats up a ton of spectrum space. It's a total bandwidth hog. Plus, FM signals don't travel nearly as far as AM signals, which is why they're used for more local, line-of-sight stuff at much higher frequencies.
And that brings us full circle, right back to where we started. You really do find FM all over the place. Obviously, there's FM radio, but it was also used for the sound in old-school analog TV. And maybe most critically, it's the technology behind the two-way radios used by police and ambulances, people who absolutely need that super clear, noise-free communication to do their jobs.
So that leaves us with one last question to chew on. FM is this amazing, robust, brilliant piece of analog tech. It's served us so well for so long. But now, we live in a world of digital streaming, satellite radio, and endless data. So what's the future for a classic like FM? It's definitely something to think about. Thanks so much for tuning in.